Today we'll be looking at linear regression, which is a part of machine learning. So machine learning is a subset of artificial intelligence wherein you try to help the machines make its own decisions. Say, for example, it can relate to any self-driven cars or people like robotics. They speak to you and help you answer questions. So it can be anything. So to define a subset of that is we have a little of machine learning, and we also have a deep learning. I think we will cover that module at a later point. But for now, we will look at machine learning, and today's topic would be linear regression to begin with. Before I go to linear regression, there are a couple of things that we need to brush our concepts with. So the first thing that we look at is the ground truth data type. Say if you have a ground truth, if you have a target column, which it can be a class, or you can call it as a label, or you can call it as some continuous value. Based on the type of the target column, you can choose what kind of model you have to apply. So it all starts with two things. Say we have a supervised learning. Whenever you have a ground truth, it can be a class or label or a continuous value. And there are a couple of cases where you do not have a specified class, but you still want to apply machine learning to capture the patterns, underlying patterns. It can be used for your business decisions and improve your revenue and all. And we also have reinforced learning, wherein we have continuous training, and based on the decisions made by the machine. If the decision made is good, then you'll try to reward it. If the machine makes some mistake, you'll try to penalize it. That is called reinforced learning. For now, we will be looking at just these two topics. I think the reinforcement learning is more of a Gen AI kind of a concept that can be covered at a later point. But for now, we will stick to supervised learning and unsupervised learning. The key takeaway is that whenever you have a target variable, say for example, we have a data set, and the data set speaks about whether the loan was given to a person or not. So if the loan is given, the it would be of class 1, and if the loan is not given, it would be of class 0. So it is a categorical data where you have two features, or you can say you have two classes or two labels. So in this case, because you have ones and zeros, it would be a classification problem. And whenever you have a supervised learning, you have something called as ground truth. So no matter what, the ground truth is an event that has occurred, and it is going to remain that. Say for example, you have a 5 rupees note here, and if I show this 5 rupees note to any person across the globe, they can identify that it is a 5 rupees note. And the machine can come up with by saying, say it is not 5, maybe it is 6 or maybe 8. It can make mistakes, but the reality is it is 5. So ground truth, in other words, is what is the real value, what has actually happened. So it is the actual value of that particular record. Okay, in this case the image is 5. And as I said, the ground truths can be categorical values or a continuous values. If it is going to be a categorical value, you will apply classification models, and if it is a continuous value, we will apply a regression models. On the other hand, we also have something called as unsupervised learning. Okay, this is where, when you do not have any kind of yes or no, say you do not have any classes, but there is some underlying pattern for which we can make use of that underlying pattern to improve our decision making. Say for example, this data set that you see here, let us say it belongs to some revenue management, and wherein you have your revenue and you have your customer satisfaction. So this cluster here is the ones which has highly satisfied customers, and the revenue is also very high. But this cluster on the other side is having low customer satisfaction and low revenue. So if you want to improve your business model, you have to come up with some kind of a products which can push the people from this cluster to this cluster. Slowly, even this to here and this to here. So what you're trying to do is you're trying to make analysis based on the given data set, and then you're trying to make some decisions. So instead of you making the decisions, you're trying to help the machine achieve this clustering problem. So I want to understand which are the customers that fall to this cluster and which are the customers which fall to this cluster, and what is specifically happening in this cluster which is having a very good revenue, and what is happening in this cluster which is having not so good revenue, not so good satisfied customers, and so on and so forth. Okay, so you have supervised learning and unsupervised learning. Supervised learning is something where you have the ground truth. It can be classes or it can be a continuous value. If the target column is categorical data, we are going to apply a classification model. And if the target variable is a continuous data, we are going to apply a regression model. Okay, that is for the supervised learning. And unsupervised learning is more like a clustering technique, or to find out which clusters, how many clusters we can make, and different ways to do that. Okay, so let us go a step ahead and we will look at supervised learning in linear regression. Right, so if you go to linear regression now, so as I said, this is a point where you have a data set with a continuous target column. So my target variable is a continuous data. So when I say continuous data, what I mean is, say for example, we run a retail store, and my data set says for a given item what was the history like. Say for example, I have a data frame which says what is the item, what is the package value, what is the price, who was the vendor, where was it stored, and how much quantity was it sold for. Say for example, how much did I buy, and how much did I sell for, and so on and so forth. So the whatever you look at the sales column is what is going to be my target, and I want to predict what might happen given a case. I want to check for the next month. Say for example, I want to check at what could be the sales for August, so that I can buy necessary items and keep it stocked in my warehouse or my distribution center, and so on and so forth. So now linear regression is going to be helpful in applying on such data. Whenever you have a continuous target column, we can use linear regression. So what is linear regression? Okay, to begin with, let us discuss about something called as linear algebra, I think, which we might have heard during our school or college time. Okay, the linear itself is something like a straight line. It means that it is straight line. It can be a line or it can be a hyperplane. It can be anything, which is pretty straight. Okay, and you have couple of features. Say for example, you have feature 1 and you have feature 2, something like this. So let me, instead of drawing, let me show you in the slide. Say to begin with, let us take that we have a two-dimensional space like this. As you might have remembered, this is our x-axis and this is our y-axis. Okay, and then what we're trying to do is we are trying to identify a couple of points around us. Let us say that these are the points, and each point will have its own x and y coordinates. So you have like 3 points, and because we have 3 points which are following the same line, we might come up with a line like this. How to know if all the 3 points belong to the same line is by calculating its own slope. So what you would have is the slope here, for example, this is a slope. You will have some value. Let us say it is m. You will have the same slope here also. The value will be same. Even in this case, it will be same. So no matter which 2 points I take within the line, it will have the same slope for all the points on this line. And the intercept at which, say for example, if my x becomes 0, what is my value of y? This becomes your intercept. So how to calculate the slope value of a given straight line is simply find out the difference of y's and divide it by difference of x. Say for example, in this case, my y value is 4, and in this case the value is 2. So 4 minus 2 divided by 6 minus 2. 6 minus 2. So in this case, your slope value is 0.5. Okay, similarly, what is your intercept? Say, for example, this could be a 1. So the intercept is 1. So your equation becomes y equal to 0.5 of x plus 1. So this is how your equation is determined. Why we are discussing this, I will let you know in a couple of minutes. But for now, if there is a relationship between x and y, and if the relationship is linear, then we might have something of this kind of a straight line. There are a couple of assumptions. Now, what are the assumptions? Like, we are trying to reverse engineer from this particular line. Okay, what we did so far is, because we took 3 points, and out of the 3 points, I came up with this equation. Now I want to reverse engineer. Given that I have this equation, can I predict what is my y for a given value of x? Say, for example, now here the value of x is 2, 4, 6, 8. So here the value of x is 8. So what is my y value here? I'll simply go and substitute it. So 8 into 0.5 is 4. 4 plus 1 is 5. So you might have somewhere around this. This becomes a point. So if this becomes your model and you have an independent feature, you can predict your target column. In order to find out whether there is a relationship between x and y, there are a couple of concepts. Okay, so let me just move forward. So far we have discussed about slope. The way we find out slope is by simply taking the difference of y2 minus y1 and divided by x2 minus x1. That becomes your slope. And your intercept is something where, the given a case where x is 0, what is my y? And this becomes my equation. So far so good, right? This is a linear equation. Now I want to apply the same concept on a data set. Now I want machine to find out this kind of an equation, so that once the machine finds this equation, I'll simply put on my x value and I can get what is my value out of for that particular x. Now this x can be a feature from future. Okay, so for example, I go to 1st of August. I go to 1st of August. So what will happen, given a case that my date is 1st of August, what is my sales gonna look like? Or say, for example, given a case that a person is drawing a salary of $100,000, what is a chance that how much loan can he look for? Okay, that is what we are trying to solve. So if you have a model like this, you simply have to put in your x features and get your y features. Okay, let us move ahead. So one thing which we need to keep in mind is, we have to find out the relationship between x and y, and that relationship is determined by these two things: your slope and your intercept. Okay, so how to determine if there is a relationship between two variables or not? Say, for example, if you have height and weight, if they are related or not, how do you determine? So we know there is something called as variance. Okay, in the class of statistics, we have discussed something called as variance, wherein variance is a measure or spread of a data point around its mean. So if you have a continuous data, and if a mean is somewhere here, it determines how spread the data is around the mean. This is variance. And how you're calculating it? You're simply dividing, you're simply taking the subtract of x minus xi, sorry, xi minus x bar whole square. And you might have to sum it up. This becomes a variance. So it is a measure of spread. And if you want to calculate a standard deviation, you simply have to square root it. Now I'll discuss a little next step of this. So just like how we have variance, we have something called as covariance. Okay, let us talk about one feature first. Say I have one column which is height, and I want to understand how my height is behaving around its mean. So for that single feature, I'm going to use variance. But if I want to check the variance of height when I consider weight also. Given a case when I consider weight also, then how will the variance behave? So in that case, you will be having something called as covariance. It is nothing but the product of both the attributes. So you have your weight and you have your height, and you're dividing by something like n minus 1. So we are dividing this by n minus 1 only to increase the value so that it will try to boost up the value to as high as possible. And then what will happen is you will try to come up with some big number. This number can be positive or negative, ranging from infinity to infinity. Given a case that a number is positive, we can say that x and y are positively related. So if increase in x, it also increases the y value. So increase in x will also increase the y value. On the other hand, if the covariance is negative, something like this, you will have the relationship on the reverse order. So if x increases, my y will decrease. This is about covariance. When there is no relationship between the variables, say I have weight here and I have temperature. So given a case, I have weight on my x-axis and the temperature on my y-axis. I can say that it will have some kind of a straight line where the temperature is like 32, 33, or 27, and so on and so forth. So indirectly, what would it mean? That the covariance will be as close as possible to zero. I mean, it will be very close to zero. Means because there is no relationship between temperature and weight. Okay, so just keep this in mind. If covariance is positive, there is a positive relationship, and if covariance is negative, it is a negative relationship. When I say positive correlation, it means that increase in one feature will also increase the other feature. Increase in my x will increase my y. Here, increase in my x will decrease my y. That is about covariance. Now, covariance also has one issue, is like it'll not get rid of units. Say for example, you have weight, so it will be like kgs, and you have height, it will be like feet. And there is a scale problem in covariance. Now, when I say about scale problem, if I convert this kg to grams, 1 kilo will become 1000 grams. Say for example, so a person with weight of 65 will become 65,000, for example. Okay, so when I go and find this number, when I go and multiply this, say instead of feet, I go and put centimeters, say maybe 160 centimeters, the number of product will become very big, right? So this number can range from minus infinity to plus infinity, and this big number does not say anything. It is only the sign we have to look at. If it is positive, it is this. If it is negative, it is this. But the value of that number has no sense. If you want to understand how strong the relationship is, that is where you have something called as correlation. So we discussed about covariance, where you're trying to look at what is the effect of one variable on the other variable, and you want to understand how strongly they are related. What is the magnitude of that correlation? Then you have something called as correlation. Here we're simply finding the covariance, and we are dividing by standard deviation of the respective variables. Then what would happen is, because you have units on both ends, say kg, sorry, you have grams, no? So for example, I have grams and I have centimeters. Here also in the denominator also you'll have grams and centimeters. So they will eventually get cancelled. So correlation has no sign, but it has direction, -1 to +1. It still has direction. So higher the value, the closer the value to any of these numbers, the better the relationship is. So if I say the correlation is +1, then x and y are very highly correlated. you will find a 45-degree angle. When I say 45-degree angle, it means that for 1 unit increase in X, there is 1 unit increase in Y. They're highly correlated. Every data point is correlated. On the contrary, if the sign is negative, you will have something like this, -1. You'll have something like this. For 1 unit increase in X, there is 1 unit decrease in Y. This is how it behaves. So if the correlation value is anywhere between 0.7, 0.8, 0.6, then you can say that there is some magnitude to that relationship. Okay. But just by looking at correlation and covariance, it is not sufficient for us to determine if the relationship is really genuine or it is just in case. Say, for example, we have increase in sale of ice creams. And whenever there is increase in sale of ice creams, there is also increase in heat strokes. Okay, let us talk about a region where there are a lot of sunlight. And whenever there is an increase in sale of ice creams, there is increase in heat strokes. So these might become very highly correlated because increase in ice cream is also having like here also there is an increase in heat stroke. But they might not be having a causation because like say whether if I go and buy ice cream, does it mean that I'm going to get heat stroke? No, right? Because it doesn't work like that. So there is something called as causation that you should be looking at. Is X really having an effect on Y, or is Y is being affected by X is really what we have to determine. And who is affecting whom? That is the main question. So in this case, the ice cream and heat strokes, in this case, there is a third party variable that is nothing but which is not in the picture. It is like the season. Okay. So because it is a summer season, there will be tentatively higher amount of sale in ice creams, and maybe people are getting dehydrated also, and simultaneously some amounts of people are also getting heat strokes. So it doesn't mean that this is causing this or this is causing this. So in this kind of issues, you cannot apply machine learning models. Okay, because that is a problem for us to determine first which is causing what. Only then the machine learning model can really gauge the issues and come up with predictions. So far we have covered a couple of things. What are the couple of things? We have looked at covariance and correlation to determine if there is a relationship or not. And then there is something called as causation. We have to really know that Y is being caused by X and the reverse is not possible. Reverse is not true. And we also saw the linear regression equation, wherein you have Y is equal to mx plus b equation. And for coming up with that equation, we have to find out what is our slope value and what is our intercept value. Okay, so far so good. Now let us go a step ahead and look into what linear regression has to say. So linear regression is also around this, wherein you have a couple of features. Say maybe for now, let us take one independent feature and one dependent feature. Let us say that there is some positive relationship amongst these variables, and the relationship is in the positive direction. It means that when my X increases, my Y is also increasing. That is why you see some angle to it. Now, if I have to train the machine and help me come up with these values, if I give an X value, what is my Y value? Can it go and predict? So in order to predict what the machine needs, we simply need to find out this kind of an equation. This equation is similar to Y is equal to mx plus b, correct? Mx plus c, correct? It's the same equation, but you have different, you do not have m here and you do not have c here because it is not exactly straight line, and you're trying to approximate it. You're trying to find some kind of a model which will make errors. It's okay. We are allowing the model to make errors, but we want to make as less as possible. We don't want the model to make too many errors. We allow some error to happen. So in order to come up with that model, we have to identify what is my relationship between X and Y and what is my intercept. Okay, so again, if you want to find out the beta 1, we can apply some mathematics and we can come up with that value. You don't have to worry about the formulas, but the key takeaway is we have to find this model which can represent this equation, correct? Now, in order to represent this equation, there are two things that we need to find out. What is my beta 1? What is my beta naught? These are the two things that we need to find out. Now, the next question becomes which model it should be. Now, all these models are correct. When I say model, it is nothing but a linear line. So all these are correct. Red line is also possible. The blue line is also possible. The light blue line is also possible. So for example, all these are possible. So which of these should be my model? So if I change my line, the slope will also change, the intercept will also change. And based on that, my prediction will also change. So we have to make sure that we choose a model which makes less number of errors. So how to tell errors? Say for example, I apply some kind of a iteration thing. I try with random values of beta 1 and betas, and I come up with this equation. Let us say, for example, this is my equation which is going to represent my model, and the actual ground truth is somewhere here, and the predicted value is somewhere here. If you notice, what is my predicted value is nothing but, in the previous slide I showed you that there is something called as y hat. It is y hat because it is a predicted value. It is not the ground truth. Okay, and beta 1 and beta naught are something which we have to find out, and based on those values you will come up with some y hat, and y hat is somewhere around this actual ground truth. This is my actual ground truth. This is my predicted value. So the difference between them will be my error. So let us say I have two values now. The first value is 5 and the predicted value is 3. Second value is 8 and the predicted value is 6. So what would happen? This is my ground truth. Okay, this is my ground truth. So 5 minus 3, it becomes 2. 8 minus 6 becomes minus 2, for example. So when you sum it up, it becomes 0. So just mere difference will not help. So what we'll have to do is we have to square it up. So when you square it up, this becomes 4. This also becomes 4. And this becomes 8. The total becomes 8. So sum of squared errors, which is nothing but your SSE, is a square difference of your y hat and y. You have to choose a model in such a way that this value of sum of squared errors is as low as possible. Lower the value, better is the model. That would be the goodness of fit, or we can call it as line of best fit. So let us say that we have figured out the value of slope beta 1 by applying this formula, which is nothing but your covariance formula, and say something like covariance formula, and then you try to come up with this applying your mathematical formula, and then you're coming up with this beta 1 value. Similarly, you'll apply some calculus, and then you can also find out beta naught. Let us say that we have arrived at it. You technically, we don't have to technically go and put formulas and come up with this. We have standard libraries, and it will be a simple one line wherein you try to import it and you fit it, and the model will do all of this. But we have to understand what is happening inside the model. So for example, if you come up with this beta 1 and beta naught and you already have a model, how should I determine if that model is good enough or not? What are the key steps that we need to keep in mind? Okay, just before I go to the next slide, this sum of squared errors is also called as the cost function or the loss function. Based on this, my model is going to train. And how it is going to train? It will try out with different beta 1s and beta. So it will apply different betas, say let us say from 1 to 1.5 and so on. It will try out, and whichever is having the best outcome, and for which the sum of squared errors is less, let us say it is going to fix it. And maybe this optimization is happening within linear regression. So just keep that in mind. We have to find a model which is going to have the least sum of squared errors. Okay. So let me go to the next slide. Let us say that we have find out beta 1 and beta. So we have a model and we want to understand if this model is good enough for making my predictions or not. So how do you determine if the model is good or not? So we have to look at sum of squared errors, which is nothing but coefficient of determination or R square or Pearson correlation thing. And looking at this R square, higher the R square, better is the model. Okay. And just keep this limited to linear regression and also to one dimension space, because there is something called as adjusted R square, which we'll learn about in the coming sessions. But for now, let us say whenever you have just one variable and one target column, then R square can be looked upon directly without having any doubts. Now, what is this R square? Now, we discussed about variance, right? Now, variance is something wherein it is trying to measure the spread around the mean. So how scattered the data is around its mean, that is variance. So R square is something like that. How much of variance present in the data can the model explain? Now, for example, if you take a case wherein you come up with this model and all the data points are on this. Okay, all the data points are on this. So in this case, the R square will be very close to 100. Say it is like 99%. So it means that it is able to explain 99% of the variance of this data set. On the other hand, if you have a data set which is pretty much like this, and your R square is like this, it will be 0. R square will be 0. In this case, it means that your model is unable to explain any variance of it. Normally, if the model is good, you will find R square greater than 80 or 75. 100, I think it might not be possible with real data sets, but just in case, if you get 100 also, nothing to worry. But you see that anything above 80 is a good model for us. But again, I'll just keep this in mind that whenever you have R square close to 1, it means that there is high possibility that your model is getting overfit. When I say overfit, it is trying to capture all the patterns in the history. It is trying to capture all the patterns in the history. But when it sees an unseen data, let us say we are in the month of July, when we go to August, and when you try to apply this model, then it miserably fails. In August, let us say your actual value is somewhere here and your predicted value is somewhere here. It fails miserably. So this is where we will have a concept of overfitting, but we will discuss that at a later point. But for now, when somebody asks you about what is R square, it is simply that how much of variance does the model explain for a given data set. Okay, just keep that in mind. And higher the R square, better the model performance. And then we have something called as some other steps that we should be looking at. One is the R square. And after checking the R square for the given model, whenever we are applying linear regression, there are key things that we need to keep in mind. First thing is that there should be a linear relationship. Of course, it is a linear regression. So if there is a linear relationship, only then you can apply a linear regression, right? So in this case, what is happening is you have an X and you have Y. So if there is a linear relationship, only then this model can be applied. If there is no linear relationship, I think the model cannot be applied. Okay, even if you apply it, it will not be robust. And the second thing is that the model should be making random errors and it should not have any patterns to it. So when I say pattern, let us say I have a time here. This is my time. When the time can be anything, it can be days, it can be hours, it can be months. So when you notice any patterns of this, like this, it is periodically making increasing errors and decreasing errors. So this is a pattern. Okay, this is pretty much random. So if you have errors that are being completely pattern, it is it is, then it means that the linear regression is not the right model for it. Maybe because if it is time dependent, it is most likely your time series problem, like wherein you can go with models like ARIMA X, and so on. But for now, because we are starting off with machine learning and we are applying a base model of linear regression, I should make sure that the errors are pretty much random. It should look like this. So errors, when I say, it is the difference between your ground truth and your predicted value. So the predicted value is referred as y hat and the ground truth is referred as y. And the difference is pretty much random. And also the difference should be homoscedastic. So when I say homoscedastic, it should be having a constant mean. So if you have a heteroscedasticity, then you would have something like this. Generally that occurs when there are outliers. This is heteroscedastic. And this is homoscedastic. Okay, this is the third assumption. When if you want to make sure that the linear regression will work out very well, then the error term should be homoscedastic, not heteroscedastic. And the last but not the least, the error term should be uniformly distributed. So when I say uniformly distributed, what you're going to do is, like, you have a continuous feature. Say for example, you take any normal distributed value. In this normally distributed value, you can take the quartiles, the Q1, Q2, Q3, and Q4, right? You have 4 quartiles. Now for this normally distributed, you will go and compare it with our errors, right? Whichever errors that we have made. So we'll make sure that the dense is equal among these. So the density here and here between Q1 and Q2 is same, Q2 and Q3 is same, and Q3 and Q4 is also same. So that is when you'll find this in the quartile part, you'll come up with this straight line equation. So let us say if there is no straight line, you have any line like this, it means that it is not a linear regression model, or the 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 use case will not be applied for linear regression. So for linear regression, you need to find that all these are getting satisfied. If all these are getting satisfied, your linear regression model is going to work very well. If they're not getting satisfied, say for example, if you have some deviation out of these assumptions, then of course you can train any model if you want, whichever model you want, the performance will not be as expected. Let I go back to a point where I discussed this straight line. Sorry, here. Okay, let us say that there are a couple of people. Now this is my weight and this is my height, and there are a couple of people who are kind of outliers. Now this is one cluster which are not following a healthy diet, so their weight is pretty high, but their height is not increasing. And also a couple of other people wherein you have like this. Maybe these people are kind of obese, and they have some medical issues, and due to which their height has not increased, but the weight has completely drastically increased. So when you have this kind of a data set, what would happen is when we try to make up a model, the model will try to balance even those things. So it would become like this. Given a case that the data did not have these kind of outliers, then the model would have been very perfect like this. And it can predict almost all the values with minimal error. Of course, error will be there. I don't say that there will be zero error. We are trying to approximate it, and just by approximation, we can solve a lot number of problems in the real world. Okay, so in order to make the model as robust as this, we need to make sure that in the pre-processing you handle all these kind of outliers data. Only then the values will be very good, or the linear regression model will be very good. Okay, so these were the couple of things that we had to look at in linear regression, but there are more values to it. Say for example, you already saw what is R square, and you saw that these 4 lines are, these 4 assumptions are properly followed. What are the other things that we can look at? So in the next section, probably I will tell you there is something called as P statistic for a given feature. Say if you have X here, for X, if it is able to help you find out a model, it will have something called as P probability value. And this probability value will range from 0 to 1. And there is also something called as F statistic. If your model, if your independent variable is having less than 0.05 of p-value, it means that X is really having an effect on Y. Okay, if the value is not less than 0.05, what I mean to say by 0.05 is, if you remember our class of confidence interval, right? We had a uniform normal distribution and we had error terms on both ends. So you had 2.5 error on the left side and 2.5 error on the right side. What this p-value signifies is 95% of the cases, if the value is less than 0.05, 95% of the cases, X is having an effect on Y. Means it can be present anywhere within this 95% confidence interval. So you have to look at a p-value to determine if X is really having an effect on Y or not. And then F statistic, stating your model is significant or not. Statistically, your model is good or not. So your F statistics should also be looked at and P values should also be looked at. But we'll look at these values when we go to the programming part. I will touch base on more concepts around this probably in the next session, but I think we should be good for now. Thank you.